morning. So this is Gajendra Shekhawat. So I'll be talking about some of the functional aspects uh, of the AFM imaging that includes Raman spectroscopy and nano IR, because I have seen that over the years. Um, if I go long back in the history of the AFMs within this facility, almost 10, 15 years back, we have seen that more people are interested in doing the surface morphology. They just want to know what is the surface roughness, how the 3D structure looks like, how the resolution looks like. Now, in the lately last 5, 10 years, things are moving more towards more quantitative, more functional, and then also the integration of AFM with chemical IDs. So basically, there is a rapid advancement in the AFM technology, and I'd like to share a few things with you. And then all of these things are within the facility. If you look at the AFM 50 years back or 40 years back, this is a typical AFM that was developed by the original inventors. So you can see here a bunch of wires, and there's a probe there that interacts with the surface. So this is basically a handmade things of scanning tunneling microscopes. So the connection looks very hard to figure out which is the probe, which is the sample. And then they image the first. They use the graphene. They use the Scotch tape. Lift the layer on the graphene, and they see the atomic structures of that. Okay, so this is the first image that they, I think, did in 1986, and then this is how a little better version of that system. Maybe after a few years, you can see here how the scientist is basically putting the probe and then the sample within the setup. Now that is part of the history now, and that is basically the system is back in the Museum of London. So if you go there, you can see around that. Now, basically, I will come on the actual functional imaging and the spectroscopy. So the AFM, many of the people, they are not familiar that, they think that the AFM can do this surface morphology, surface profile, surface roughness measurements. And then many of them are still learning, and some of them they are aware that the AFM can do a lot of other things than the surface imaging, surface roughness. So here, basically, you can see the different components, more like a quantitative components of the AFM imaging, where you can do electrical measurements, and within the electrical, there are different techniques and methods. The mechanical measurements, mostly the mechanical measurements are confined to the surfaces. If you need to do a bulk mechanical measurement, then obviously you have to do the indenter type systems. Then you can also do some nanofabrication. So basically, deep pen lithography type tools are there, so you can do these things. And then you can also extract some chemical information, which comes under the category of nano Raman or nano IR systems. So thirst imaging also a component of the Raman, where you can resolve things down to a few nanometers as compared to a conventional Raman spectroscopy, where resolution is limited to the diffraction. Okay. And then we have a thermal also. So basically, you can go down to a resolution of few nanometers with these thermal microscopes. So I'll be talking about the different components, Kelvin probe microscopes, conducting. So you can see here, there's a list of different techniques that we have these techniques available within our facility, and some of them may be installed in a couple of weeks. So going there, everything, basically the basic principles, peak force tapping, because that peak force tapping is mostly used in almost all of these techniques. So the peak force tapping is basically, you modulate the probe with a very small amplitude. Typical the frequency is 1 to kilohertz. And then the feedback signal is basically the peak force between the tip and the samples. It allows you to directly control the forces. So when the probe is interacting with the sample surfaces, your force are basically almost few piconewtons. So that will allow us to not damage the surface and precisely measure the surface properties, which can be electrical, magnetic, or whatever. So that's the basis. And then the peak force quantitative nanomechanical mapping that we have allows us to measure the mechanical properties of different materials, whether it's a composite materials or polymer materials or cell biology. So basically, we can go for a wide range from very soft tissues to the materials which are higher modulus. So the only thing is that what we have to do is basically we change the configuration of the probe or the stiffness of the probe. So we have to select a proper probes of proper spin constants to measure the mechanical properties of these different materials. In this case, you can say we can go even like to a few pascals to gigapascals range. And then this is a force separation curves that shows that the different components you can measure with these techniques. You can measure the modulus, you can measure the dissipation, you can do the adhesions and all those things. And you can quantify these things with certain calculation. The inbuilt algorithms within the software allow you to directly measure that. Few calibrations are required in terms of the tip radius, what is the spin constants and all those things. Then you can see a typical example where you can see you can get a height profile, you can get a modulus, you can get a deformation, adhesions, or dissipations. So if you have multi-phase materials or viscoelastic materials, then you can see the different contrasts within the image. Based on the different stiffness, you can get a different contrast. So basically, you can identify this. So this type of technique is very useful, especially if you have monolayers or if you have very thin films that you cannot go for a bulk indentation. And bulk indentation has certain limitations that you cannot indent like pretty close to the surface. So there's a certain criteria over there. So to minimize the substrate effect. But this technique is pretty useful, very powerful. So you can have some monolayers or some nanoparticles on the surfaces. You cannot eliminate completely, but you can try to avoid some substrate effects in your modulus calculations. So we have these techniques in almost most of our AFM systems. Then mostly it comes to the other techniques that we have the magnetic force microscopy. So in this case, typically we use a magnetic probe, and then we basically magnetize the probe. There's specific folders that we use. So in the case of a magnetic force microscopy, you typically use a tapping mode type technique to collect your topographical profile. And then you can lift the probe to a certain height, depending on how much you want to lift. And then the software turns the feedback off. So you are moving at a constant height. So while you're moving at a constant height, there's an AC signal applied to the probe. So if there's a magnetic interaction, then basically that shifts the frequency, and then through the phase and amplitude change. With that frequency shift, we can identify the magnetic domain structures within the different materials. And you can even try to detect a pretty low magnetic field here. So here we have demonstrated back, we can detect features, 15 to 20 nanometer resolutions. So this type of technique is also available here. Then when it comes to the different other techniques, there's a electric techniques available. So we have electric field microscopy, we have Kelvin probe microscopy. So I will go over few of them. Then we have a conducting AFM, we have a tunneling AFM, we have a photoconducting AFM. So we used to have a photoconducting AFM on the AFM system, but right now that is available on a Raman systems, because then we can use 4 different lasers, and then we can excite the lasers on the samples and measure the current, either it's a dark or bright current. Then the impedance, capacitance, resistance, this type of things is coming next month, and that technique we will be getting next month. And then basically there will be a seminar and different demos. So I will not talk about those things. I will leave it to the Bruker application scientists who will come here to show us these techniques. And then we also have a piezo response force microscopy. A lot of people are using it, so you can measure some ferroelectric domains and all those things. Kelvin probe is more popular here. So basically, again, it's the same thing. You use the tapping mode image to basically collect the topographical profile. Then you can turn the feedback off and you can apply a combination of AC and DC bias on the probe. Okay, so the cantilever is only driven with electrical forces during the lift, which is a combination of AC and DC. And when the DC bias, so when the cantilever interacts with the sample, there's electrostatic forces there because of the sample. There's a certain features on the sample. And then the whole idea is that DC voltage, this feedback system applies a specific DC voltage to nullify those electrostatic forces, and that is basically the contact potential difference. Okay, so if you are imaging some metals, we can measure the work function. So if you are imaging some semiconductor, that contact potential difference is basically the change in the dopant profile. Okay, so that you can measure with the Kelvin probe microscope is a very simple technique here. The systems here allows us to automatically change the parameters and all those things with a little manual settings. You can see a different examples here. So on the left is topography, is a surface potential. On the right, you can see here, this is regarding the nanowires. On the right, the different layers on the graphene. So you can see based on the work functions of these different layers. On the right side, you can see the contrast in the images looks different, okay, because of the change in the dopant profile. So these things you can measure with these things. So there is also a conducting AFM setup we have. We have both conducting and tunneling AFM. So conducting AFM is basically is a contact mode type of technique. Okay, so measures the conductivity on the surfaces. So mostly you should not have insulating samples. You should have conducting semiconducting samples, and we apply bias between the probe and the sample, and then you can measure the current. It's a very simple contact mode techniques. And then the ranges are like few tenths of a nanoamp to 100 nanoamp. So this is the range we have. If you want to have a low range, if your sample has a pretty low currents, then you can go for a tuner type, which is tunneling AFM, where you can have a large range of your options for the current. You can go for a very low current, like picoamp, something like that. It still uses that peak force techniques. I explained that in the beginning. So this allows you to have a lower contact force within the tip and sample because these modes uses conducting cantilevers, which are typically comes with a high cost. So if you lower the contact force between tip and samples, you can lengthen the time of those probes, and also you can have a better resolution. But the choice is between the users, what type of techniques they can use. Here is a typical example. As I explained before, you apply the DC bias between the sample, you measure both topography and the current, but you can also do imaging spectroscopy. You can also do basically imaging in the current voltage spectroscopy with these techniques. So you can measure the breakdown voltage and all those things in these, especially these metal oxide layers, materials. So it's a very straightforward technique. Then the peak force tuner here, you can see basically if you have carbon nanotubes or different other materials, soft materials, where you want to measure the conductivity, you can do this. So these are different examples. But one of the advantages of the peak force tuner is that you can have multiple multimodal imaging, basically. That means you can do height imaging, you can do modulus imaging, you can do adhesion imaging, and also you can do the conductivity map. So you can have a multiple properties, at once. So that's the advantage of peak force tuner type things, which is not possible in the conducting AFM. Okay. So it maps the most electrical magnetic property, but you can also do the spectroscopy with these type of techniques. And then there's an option for a photoconducting. Now, since we have this setup now on the Raman system, so mostly we are switching whoever wants to use this. So mostly they can get trained on the Raman, because then we have 4 lasers on the Raman system. You can control the laser powers. And because the Raman system is integrated with AFM, so you can basically measure these photoconducting properties. You can still do terse imaging. You can measure the Kelvin probe or conducting AFM. So everything can be done together, and you have ability to control the laser power. So this type of technique is very useful, especially for solar cells or perovskite materials. And then we have these facilities in our setup. Okay. I'm not discussing about the scanning microwave impedance spectroscopy because there's a seminar here by a Bruker application scientist on April 1st, 11 to 12. And then they will talk about the scanning microwave impedance spectroscopy, where you can measure the permittivity of any materials, you can measure dielectric constants, or you can measure the conductivity. And then it's a near field mode. You don't need to physically touch the sample. And then they will also bring some scanning capacitance microscope, so you can do a dopant profiling and the scanning spreading resistance microscopes. It can also measure the dopant profile or the resistance of any type of materials. And then they will be here for 4 days after the seminar. The system will be here in the AG71. So you can basically come, and so I will be contacting the users who are already familiar with these setups, especially the conducting part and all those things, mm, to set up a sessions individually with them and go over with them, with their specific samples or any other technique they want to learn from them. And then the people who are not using currently the conductivity and other setups within the SPID facility, they are welcome to email me to set up a session with them. So basically, they will be here 4 days. So we'll be running a lot of samples and a lot of interactions with the people. So they are here on site. So please better utilize their times and all those things. So because we are putting more and more efforts towards the functional capabilities. So it's very important that users can also interact with the application scientists. Then I will touch base a little bit about the dimension icon IR spectroscopy systems. So this system will be here maybe in a couple of months because we already placed the order, and then we are trying to acquire the system. So that will be still placed um, in where the fast scan right now, it will replace that space. So nano IR system is basically a combination of a full highly advanced icon AFM system. So the nanoscope 6 controller, so you can do more high speed quantitative nanoscope imaging, but it will be also integrated with lasers and other things. So you can do a chemical spectroscopy down to 10 nanometer resolution. So you can basically do a lot of these things and different applications, pharma, thin film, semiconductors, solar cells. It has a wide range of applications. I know most of you are using here the FTIR in the KEC facility. So FTIR spectroscopy is also provide pretty good information about the chemical, but it has a limitations on the resolution. So that's what the nano IR is a very powerful technique. So basically here how it works is the IR pulse, arise with the cantilever surface. So the sample absorbs that and heats up and expands, and that basically disturbs or perturbs the mechanical interaction of a probe in the surface. Okay. So the magnitude of the force is basically proportional to the absorption coefficient. So you will get the spectrum. It's a very straightforward technique, but given that we use a very high resolution AFM probe, so basically the resolution is down to 10 nanometer. So you can see one technique, but you can have two ways to integrate your samples. So you can do spectroscopy, where you keep the probe fixed in space and you scan the IR wavelength. So you can get an IR spectroscopy at the nanoscale. And then, but you can also keep the IR wavelength or infrared wavelength fixed and you scan. Basically, you can get a chemical mapping along with the topographical imaging. So you can do both of these things with this technique. And then it's a very, very highly sensitive, it's a more correlative microscopy type, because here you can do nano IR imaging or chemical mapping, you can do electrical mapping, you can do mechanical mapping. So all of these techniques that you can do it separately on this system, you can do it together. So because it is integrated with icon system. So Icon system has those capabilities. So that can be done here on this system. And then we are also working on acquiring the laser, which has a large range. Okay, but there are three components, the QCL, which is a quantum cascade laser. So the 764 to 800 is a fingerprint region. Then you can have a different in the middle. You can look for triple bond and conjugated systems and other groups. So the laser that we are acquiring right now is going from 800 to 1800, but we are also trying to acquire another laser that goes beyond that. So what are the applications? As a polymers, life science, environmental, pharmaceutical, material research, you can count any techniques. This system is very useful. So there's no limitations on the sample as compared to the Raman test system, where you have very limitations on the sample. So you can see here this polystyrene and LDP blend. You can see the chemical IR imaging, but you can also look at the modulus, you can adhesions, electrical properties. So it's a multimodal, it's a true multimodal imaging system capabilities that can benefit many people. And then it has application for biomaterials. Here you can see the liposome-based nanoparticles, so you can easily identify whether, because liposomes are the carriers, for the drug, can be encapsulated within them, so you can easily find out with this nano IR whether these liposomes are carrying those drugs or not. So means that technique can be applied to softer materials. This is another example of soft materials where you can see the topographical image, the chemical mapping of the individual components and the combined. So you can do a lot of these analysis, mapping and individual analysis with this technique. Then we also have the technique that we developed many years back here in the Northwestern, called the ultrasonic microspectroscopy, not a microscopy. So what happened in the normal AFM modes, the cantilever interacts with the sample surface. But here we launched some acoustics waves both on the cantilevers and the samples through acoustic transducers. And then the cantilever, basically the waves coming from the cantilevers is a reference. And then if there is a defects within the samples, that can delay the phase of these acoustics waves, because acoustics waves are transparent. So if there is a defect, that can delay the phase of that acoustic wave reaching at the surface. And then on the sample surface, when the cantilever is interacting with the samples, it creates a beats, a different frequency, and then that can easily get modulated based on where the defects is located. And then those are within a low frequency range, so these cantilevers can easily detect those modulated waves, and you can identify these defects. So the advantage of this technique is that you look at the surface profile, but you can go deeper and look at those phase variation coming from defects, delaminations, contaminations, cracks. So this is a very powerful technique. And then you can see one of the examples I can give here is basically there are magnetic particles enclosed in a silica core cells, and on the top there are the coatings of antibodies, certain receptors. So usually we take TMs, we do the TMs to identify the code within these core cell particles. But here you can see a topography on the top right and the top bottom left. You can see a normal tapping mode profile, and then the bottom right you can see ultrasound image where you can see those magnetic cores contrast coming from there, because we are measuring the delay, the phase of those acoustics waves. And you can see the core cells, and on the top, you can even see the coatings of these antibodies. So you can identify those things with such type of microscopy without deforming any things or doing any cross section. So this is a very powerful technique. We are working with Toyota Motor Corporations to identify the defects in the battery electrodes and all those things. So basically, I'm just presenting here one of the examples in the life science, but mostly you can do physical and other techniques. This is also one of the thing here is the scanning thermal microscopes. So the whole idea is that you can use the simple concept of AFM cantilever probe interaction, but with a certain modification of the hardware and software, you can do multiple other techniques and quantify those properties, whether it's mechanical, electrical, chemical. So in this case, you can see normal thermal microscopes, we use the two wires, they just make a thermocouples and measure the thermal conductivity, the resolution down to few microns. But here we few years back we worked with a company, and then we come up with innovative idea of using a nanoscale probe, so where the thermocouple is within the probe here, and then within the hollow probe, then probe is extended through a metal wire that's contact with the surface. So basically, the thermocouple is not influenced by any temperature variation across the surface because this is within the hollow core. So you can read these articles with more. The whole idea is that you can measure thermal conductivity with a resolution down to a few nanometers. And then it's useful, like you can do the hot spots in metal contact with the semiconductors and all those things, especially if you're putting electrodes on graphene-based materials, you can measure those hot spots. And then at the same time, you can also do temperature mapping. Okay, so this is one of the examples where we use the metal particles and then we use the RF magnetic field to heat up those particles, So we then coated these particles with certain polymers, no melting point polymers. And when the particles heated up, you can see here the polymer got melted. This is a true indication that you can measure these quantitative temperature variations with these type of technique with high resolution, which is not possible earlier. Then I will touch quickly about the third system we have. That's bringing the AFM together with the Raman PL. Here you can also do a high resolution chemical mapping, but there's the limitations on the sample here. It has to be a very thin layer of the samples. That's not, and the nano IR doesn't have that limitation, but this has a limitation. But you can have the advantage, if you have some nanotubes or nanoparticles on the surfaces, you can do this type of technique here. So you can see here, this is the normal in the middle, the normal typical confocal AFM image carbon nanotube. So obviously, we don't know whether it's a single tube, it's a bunch of tubes. So we are getting a contrast here because of the diffraction. So basically, you cannot resolve to a pretty low resolution. But on the right, you can see a terse map where you can easily identify either 2D materials or carbon nanotubes and all those things. So it's a pretty useful technique to do that. One of the major advantages of this technique is that you can also do photothermal, this photoconducting type AFMs and other AFM techniques simultaneously. Okay, so what is terse then? Okay, I think most of you heard about the SIRS and all those things. Mostly, Raman signals is typically very weak. So sometimes people have used, they used to put some metal particles, and then basically that enhance the signal, Raman signals. That's called the SIRS, but still they have a resolution limited. In the case of TERS, which is tip enhanced Raman spectroscopy, we use the AFM probes and then the incoming lasers at the pointed part of the gold coated, metal coated tips. So usually we use silver and gold, very specialized probes that create a surface plasmons and basically it's create a hot spot that magnifies the intensity of the electric field. Because the hot spots, since the tip has a high resolution, so you can get a significant signal enhancement and also at the same time the resolution. Okay, so that's called the TERS. Okay, so the TERS technique basically you scan. So this is an example of a carbon nanotube. On the right side, you scan under the surface, so you can also get both the TERS map of the carbon nanotube, and you can also get the spectral profile with this technique. So that technique is already here. This is one of the examples of a 1D materials here. Like again, the simple carbon nanotubes. You can do a TERS map and you can quantify the type of the defects present within this carbon nanotube. So basically, you can have both TERS profile and the spectral profile with these techniques. It's a very powerful technique. A little complex in operation, require a lot of patience and hard work because the most of the challenging part here is that how you can align the lasers, the Raman laser on a probe. So there are two aspects. One is a laser, AFM laser that you can align, so you can have a maintain a feedback, so you can scan the AFM topographic profile. But you have to also do the Raman laser, so that can give you the TERS profile. So this is an example of a 2D materials. Now you can calculate the defect density. You can have a spectral profile. So this, and then this is you can also do a high resolution PL. So on the left side you can see a micro PL. You can do with a typical Raman confocal Raman setup we have. But if you add the flavor of AFM on the right side, you can see tip enhanced PL. It's a pretty high resolution, very crisp image. You can easily identify. Okay, so this type of setup is here, and then we'll be ready to help you. It's a little challenge. You require little patience and little practice, And then you can do many things that we have with this setup. We have 4 different lasers. We also have the Bragg filters, or we call them as the notch filters, ultra low frequency filters. You can also call them by different names. So you can also do the Stokes and anti-Stokes, and you can also go to lower wavelength, wave number down to 6 to 7 wave number. So we have those capacities or capabilities on our setup. In the last, we can also do the biomechanics. We used to have a liquid AFM here where we can do either peak force QNM or you can do ultrasound to measure the biomechanics of different cells and tissues. We have BioSoft indenter that can measure the properties of the mechanics of tissues and all those things. With ultrasound, you can do a live cells here, so you can see on both the topographical profile on the bottom. Over a period of time, you can see how the modulus changes across the periphery of the cells by adding some stimulating agents within them. So that's a non-destructive technique, but you can also study the mechanics because the mechanical properties will allow you to get a lot of information about these cells, whether they are infected, whether they're disease cells, and all those things. Okay, so I'll end here, and then if there is any questions I can take. Thank you very much, and please contact me if you need any assistance or any further inquiries. Thank you.